Hello and welcome. In this video, we are going to begin our solutions unit. Now, we do have some background. We have gone over solutions, solubility curves, solute, solvent, saturated, unsaturated, and supersaturated, what all those terms mean in previous units. So we're going to continue now after trying to recall a bit of that with concentration, with solubility concentrations and how they're expressed in different ways. All right, so in general, a concentration of something is something that is simply the amount. Now, these will have differing values, but the amount of solute over the amount of solution. Okay, and there are three basic ways to express this that we're going to go over. We're going to focus on the third one, but we're going to look at how they can be expressed as a percentage, or we're going to see how very low concentrations can be expressed as parts per million or parts per billion. And finally, we're going to spend most of our time now and in the very short-term future, going over molar concentration or focusing on molar concentration. Okay, so first, we can express percentage concentration in different ways. It can be volume concentration, so volume over volume. It can be, and that can be in liters over liters or milliliters over milliliters. We can have mass over mass concentration, percentage expressions, or even mass over volume. Now, this is one of the more practical ones. For example, you might go to the pharmacy and buy something, let's say a children's Advil or children's ibuprofen, whatever you'd like to call it, and it's usually expressed in milligrams per milliliter, or you might see grams per milliliter. Now these aren't SI units, right? We don't use liters because we're not buying whole jugs of this, so it's not really practical to express it as a milligram or gram per liter, but instead it's more practical to use these. So this is an example of non-SI units being used in concentration. Right, so when we look at mass over volume, so grams per milliliter, you just take your gram value, your volume then in milliliters, and multiply that by 100 to get your percentage, just as you would figure out your mark on a quiz, test, or exam. So our first example is this. So a sample of road slush was gathered to analyze the concentration of calcium chloride, and its sample has a mass, so the entire thing, has a mass of 23.7 grams. Now, when the solution was evaporated, now assuming there's nothing else, there's no sand or any other contaminants in there, that it's simply calcium chloride and snow water. When the solution was evaporated, the residue has a mass of 4.58 grams. So what is a mass percentage concentration of calcium chloride in the slush? So originally we had a certain amount of calcium chloride, then we had some solid ice, or some solid crystals of water in the form of snow. So we're going to say mass. So this is how much salt we have. This is the total. Then part B, so what is a percentage? What it's asking us, part B, is then how many grams of calcium chloride would you have if you had 100-gram sample instead of that 23.47. So we're going to use this percentage from A to figure out B. And because it's 100, it should be pretty simple. Okay, so mass of solute, mass of solution, 19.5%. Right, all we did here, I think I'm missing something. There we go. Animation was delayed there, but we have 4.58 grams divided by the mass of that solution, and we multiply that by 100, and we get 19.5%. Right, so 19.5% is a concentration in mass, or comparing mass to mass. Right, so if we have 19.5 as our percentage concentration of calcium chloride, therefore in a 100-gram sample, all we do is we take this 100 grams multiplied by a percentage. Of course, you'd have to convert this into a decimal, so 19.5 divided by 100, and we get 19.5 grams. You don't even have to do that math. You know that it's 100 grams, so it's 19.5 grams. And there is your therefore statement. Okay, now for solutions that have a very low concentration, we can use two things, two expressions here. We can say that it can be expressed as parts per million or parts per billion, because it wouldn't make sense to express something in such a small number for practical reasons. So when you're looking at perhaps the presence of a certain ion inside drinking water, so fluoride inside drinking water, well, it's a very low concentration. It's safe in tap water to consume. You wouldn't express that as a percentage. It would be a very small number. So we can say parts per million, or in the water you might purchase, there might be other ions present inside. Those are usually expressed as parts per million, parts per billion. So it's the same as a mass percentage, except you're not really finding percentage. I mean, that's probably the main difference, but you're multiplying it by, for parts per million, 10 to the 6, so multiplying it by a million, and for parts per billion, you're multiplying it by 10 to the 9, so you're multiplying that by a billion. Okay, to increase that number for it to make more sense practically to express it in this larger number. So both of these, though, it's a mass of solid divided by mass of solution. Okay, so an example. So mercury poisoning occurs at 20 milligrams of mercury in the body. Okay, so express this amount as parts per million, so ppm, for a 60 kilogram person. All right, so what we're looking for basically is the mass of mercury over the mass of a person. Something to note here, this is milligrams, this is kilograms. We have to make sure those units match, right? So we've had lots of practice with the factor label method. We can convert that hopefully easily right now. Okay, right, so units need to match. So 20 milligrams, we're going to convert that to grams. Here is our conversion factor. So this is a factor label method built into the question here. So 20 milligrams, unit you want to get rid of is at the bottom here. Unit you want to keep is at the top. And we cancel out, we get this, and we get our grams at the top. Now, mass of a person, so 60 kilograms times our conversion factor. We want to keep grams up at the top of this conversion factor. We want to get rid of grams, and we're essentially then left with grams over grams, which is the idea. Now, this number is so small that if we don't multiply this by a million, it won't make a lot of sense. So we multiply it by a million, and it turns out we get a 0.3 parts per million. So we can say that mercury poisoning occurs at 0.3 parts per million. So if you were to draw out 1 million little parts, I'm not going to do that, but you can imagine. If you could draw out 1 million little parts, 0.3 of one of those parts. So 0.3 of one of those parts would be mercury. That is the amount that is needed to cause mercury poisoning in that mass of a person. Okay, now the third method, and again, the one we're going to spend the most time on, is molar concentration. Okay, here units do matter and they can't go wishy-washy like in the other ones. We need moles per liter. So molar concentration needs to be in moles per liter. So the amount of solid, whatever that substance might be, divided by the volume of the solution in liters. It can be expressed in this formula, C is equal to N over V. What you will also see, and I think I mentioned it later, but I'll do it right now, this can be referred to as molarity, right? Often big M is equal to moles over volume, right? Usually I write it this way though. Okay, but if you ever see big M, or if you ever hear the word molarity, it refers to molar concentration. Okay, example. So a saline solution, that's a salt solution. So a saline solution contains 0.90 grams of sodium chloride, and that's dissolved in 100 milliliters of solution. Okay, so there's something to think about here. This we're going to have to convert to moles, but after your last unit, you're pros at that. This can't be in mils, it has to be in liters. So that has to convert to liters, but you should be pros at that too because we know how to do that using the factor label method. So what is molar concentration of the solution? Okay, well, let's figure out moles first because we're going to use concentration is equal to moles divided by volume. We need moles, and we can get that from mass. Here's a mass, here's a molar mass of NaCl from your periodic table, and we get 1.54 times 10 to the negative 2, or 0.0154. Okay, now volume, 100 mils has to be converted to liters. So factor label again. You want liters, we want volume to be in liters. This is what you have times a conversion factor. You want to get rid of these units, you want to keep liters, and we get 0.1 liters, right? Don't have to do this every time you do a question. If you want to just divide this by 1,000, that's perfect too. Okay, so moles divided by volume in liters gives us a molar concentration of 1.54 times 10 to the negative 1, or you can write 0.15. So keeping with the correct number of sig figs, going back to see what the question gave us, it is 1 and just 1. So 1 sig fig is what you would round that to. Right now I've already explained how molarity can be referred to as big M, which represents concentration, molar concentration, and over V. Right, there's your homework. Some practice work for you to do. Post any questions. I hope this helps.